welcome. Good to see you all. Thing one. Hi, Sue. Hope you enjoyed our videos. Yeah. Thing one is, our purpose for today is going to be to do a review of the theorems that we've had, and then we're going to specifically take a look at how mean value theorem can actually be used in practice. And I will, along the way, give you a story about a friend. And then, in the second thing we're going to do, or the second thing I need to tell you, excuse me, is to remind you that you have your exam coming up on Thursday. And so we're going to do some review tomorrow and the next day. The best thing that you can do to be really ready for that is to the best thing you can do to be ready for that is to make sure that you know the official legal language of your theorems. And that you have practiced the various kinds of computations that we have done this year. And those kinds of computations are things like finding limits, and finding derivatives. Those are really the two kinds of computations that we've done. Now, there are a lot of different ways to find limits, right? You can find them from a graph. You can find them using your limit properties. You can find them from a table of values, right? Same thing with derivatives. You can find them on a graphing calculator. You can find them using derivative rules. You can find them with limit definition. So I'm making it look easy because there's really two kinds of things we need to do, but there's different ways that can come at us. Yes?
Will there be strict definition questions on these ends? Like,
there could be.
Okay.
It could be. I'll probably show up in the form of true, false. And we'll actually practice some of that tomorrow.
Okay.
Yes?
I have a request on doing it over.
Yeah.
Honestly, the only things I don't understand is what we're looking now.
Okay.
Like the mean, but can you do more examples? Because like I was doing the homework and I honestly did not know what I was looking for, and I didn't know how to necessarily show if it was not like. Okay, I didn't understand how to show if it was
differentiable or not.
Well, not necessarily differentiable. Because like I understood how to find points of differentiability and not differentiability, but I don't know how to like
check that with the mean value. How many of you can relate to what she's saying? Several of you. Okay, good. So today we can actually address that. Yeah.
Do we have to like know limits and stuff? Oh yeah.
Good question. Do you have to know how to prove anything? I will not formally ask you to prove anything on the exam. However, a lot of the knowing of theorems really comes down to knowing why they are true. So the best way to know the theorem is to actually know the proof for it. And the ones that I've marked in your study guide with a star, it's best for you to be able to say, here's the proof. If you don't, then the alternative is to try to memorize each theorem as a brute fact. And that's too much material to really keep in your head and keep straight. Okay. Any other questions, generally speaking? The format of your exam is going to be part multiple choice and part free response. And it will be, one of those sections will be calculator active and the other will not.
Will like the multiple choice be really in depth, or will they just be pretty simple? Like, here is an equation. What is the derivative of said equation? A, B, C, or D?
I might do that. I generally try to design multiple choice tests to help differentiate between students that know what they're doing and students that do not. So that if you know what you're doing, then you're going to find probably 75% of the questions to be easy. And then another 25% you might have to think about to some level or another. And there are certain formats that they follow. Some of them are as straightforward as what is the derivative of blah, blah. If y equals blah, 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 then dy dx equals blah, blah, blah. And others can be something like true or false. Now, which of the following statements is true? 1, 2, or 3. I need to know.
Sorry, I have a question about the AP exam.
Sure.
Will the AP exam kind of be like the midterm, like how there's some pre-response and some multiple choice?
Yep, that's right. It is 50% multiple choice, 45 questions, split up over calculator active and calculator not active. Then it is 2 calculator pre-response questions, 4 non-calculator pre-response questions. It will be twice as long as the midterm. Wow.
But only 45 questions? I mean, I guess that sounds...
Yeah, 45 multiple choice questions. They give you 2 minutes each for those questions. And some are, again, if you don't know what you're doing, some go like that, and others you have to think about. Yes?
Will we need a tracking paper or a protractor or ruler?
No, no, no.
Okay. Will they be
No, what?
No.
No graph calculator at all?
You don't need any of that. If there are graphs, they'll be on the page.
Thank you very much.
Oh, no, I'm sorry, no.
Yeah, if you need to graph something, the graph paper will be right there on the page.
Okay.
Waiting for you. Please, graph.
Can we get Tracy paper?
Calculator and pencil only. And no phones. Don't bring your phones.
What about a laptop?
Okay.
My PC.
So is that
What's that?
Does that be pencil? Was it like a scan from?
I don't know if you can scan it on, but what's the point of bringing it into a multiple choice? Are you perfect? No. Okay. Let's, at this time, review the theorems that we've had so far, and then we will specifically get into the mean value theorem, because that's the main story for today. We started at the beginning of this chapter with the extreme value theorem. Who knows the condition for the extreme value theorem? If what?
F(x) is continuous on the closed interval a to b, and is differentiable on the open interval.
Nope.
Okay.
Too strong. All we need is continuity. So if f is continuous on the closed and bounded interval a to b, then f of x has an absolute max, an absolute min on a to b.
Oh, that's
So, continuity gives extreme values. Continuity also gives intermediate values. That was the theorem from the last chapter, right? So functions that are continuous have 2 properties that we know and love. They have extreme values, and they have intermediate values. This is a slogan. This is not really our theorem. It just reminds us of what the theorem says. But it helps to organize when you create a slogan that's fairly accurate. Yes?
So, does that mean like the function has one absolute max or absolute mean? Or
No, it actually has and, both. So draw a picture for yourself so you can see it. If I have a function that's continuous like so, then it must have both an absolute max and an absolute min value. And also, it must have any intermediate values between f of a and f of b. That's the intermediate value case.
what if the function is like strict line?
Then it has an absolute max which is equal to its absolute max. Yep. Emily, question? All right, good. So that was the extreme value theorem. Then from that, we had a definition of increasing or decreasing through a point. So our second theorem was that if f prime of c is positive, then f of x is, if f prime of c is positive, then f of x is increasing through c. Points to the right lie above. And if f prime is negative, then f of x is decreasing through c. And that led us to an important result, which was Fermat's theorem. I shouldn't have to write all this down, because it should all be where?
In your brain.
No, where should it be?
I don't know.
In your study guide. Right.
No, that's it.
Is it? I haven't looked over the weekend. I'll check. Fermat's theorem. If f of c is a local max, or local min, a local extremum, then x equals c is a critical point. And our slogan is local extrema only occur at critical points. Notice how this follows directly from our theorem in blue right here. Because what does it mean to be a critical point? If x equals c is a critical point of f, then what is true? Or it does not exist. So, what are the only possibilities? That f prime is greater than 0, in which case f is increasing through c and is not a local maximum. Or f prime of c is less than 0, in which case f is decreasing through c and f of c is not a local maximum either. So these two theorems really go hand in hand with one another. From Fermat's theorem, we proved our, we didn't give it a name, but I think we ought to probably give it a name. Let's call it our critical point endpoint theorem. The slogan for Fermat's theorem was, local extrema only occur at critical points. Slogan for our critical point endpoint theorem is absolute extrema only occur at critical points or endpoints. And so to say that formally, we would say that if f of c is an absolute max or min on the closed interval a to b, notice I require a closed and bounded interval a to b, then either c is one of the endpoints or x equals c is a critical point of f. This is the formal way of saying it. Our slogan is, again, absolute extrema only occur at critical points or endpoints. we used our critical point endpoint theorem to then prove Raleigh's theorem. Raleigh's theorem is not going to be a theorem that I will directly test. Why? Because the mean value theorem includes Raleigh's theorem. So we then use Raleigh's theorem to prove the mean value theorem. And so that's our last theorem for this chapter so far. And the last theorem for this chapter up through the exam. So the mean value theorem is the final thing, and that is that if f of x is continuous on a closed bounded interval a to b, and also it happens to be differentiable on the open interval a to b, then there is a c somewhere between a to b such that f prime of c is equal to f of b minus f of a all over b minus a. And for the mean value theorem, there's a couple of things that you're going to need to make sure you do. One is to know the conditions very well, because you can imagine that I might ask you a question to see whether or not you're paying attention to those conditions. And the second thing is that you want to know the conclusion right here. This conclusion is kind of wordy, right? F prime of c equals f of b minus f of a over b minus a. So what is this really saying? This is really saying that the instantaneous rate of change, which is the derivative, it is also the slope of the tangent line, okay, is equal to the average rate of change or delta f over delta x, which is the slope of the secant line. So what we're saying effectively is, if f is continuous and differentiable, then there will be a point where the tangent line is parallel to the secant line. And if you can remember that concept, then you can figure out f prime of c equals f of b minus f of a over b minus a. Yes?
When you do this, I know it's a few extra seconds, but just questioning.
Sure.
When you get to, then there is a c of a to b such that f of c, prime of c equals f b minus f a over b minus a. Do you have to write the f b minus f a over b minus a before you're about to put it? Or once you put that down, say that whole sentence, then when you actually have to implement it, you have to say f prime of c equals f of 3 minus f of 1 over 3 minus 1.
Yeah, I recommend doing that because it helps keep your head straight.
Okay.
So let's actually use the mean value theorem. Heidi, let's take a look at a question that puzzled you.
Okay.
So our goal for today is to become comfortable with the mean value theorem.
Okay, f of x. Well, I don't know. Actually,
Yeah.
The f of x equals the absolute value of x plus 2
oh yeah, that was one.
On
how do you
On -2, 4.
okay, good. And just to compare and contrast it, I want to make up a different problem that you were not assigned. Let's contrast that with the same function on a different interval from -3 to 3, so that we can see the difference that different intervals might make.
I know what the answer will be, but I don't know how to explain it.
So what we're asking is two different questions. The first question that was asked is, does the mean value theorem apply? Okay. And so I need to check two conditions. I need to check, is the function continuous on the interval -2 to 4? I'm not going to require a whole lot of analysis here. Can I draw the graph of the absolute value of x plus 2 without lifting my pencil?
Yes.
Is it continuous?
Yeah.
Yeah, it is.
But how do you explain that? That's what I'm confused about.
At this level, unless I ask you to explicitly show that it's continuous, you can just assert that it's continuous and I'll believe you.
Oh. That's
Great.
interesting. Okay.
Okay? The differentiable part, not quite so much. I might have to exhibit the derivative, right? So what is the derivative of the absolute value of x plus 2? Well, the derivative of the absolute value of x is itself over the absolute value times the derivative of the inside, which is 1. And so that gives me the x plus 2, or the absolute value of x plus 2. And I can see, just looking at it, that this fraction will have a value except when x equals negative 2. Right at the point x equals negative 2. So this exists except at x equals negative 2. This is reasoning we've done for a while. Is everybody clear on that? Good? Okay. Well, now I ask, watch this question. It's really slippery. So am I differentiable on the interval, the open interval negative 2 to 4?
Yes.
Yes, because my point of non-differentiability is right there at the end point, which I don't have to worry about. So the answer here is yes. And that allows me to come to the conclusion, therefore, there is a C in negative 2 to 4 such that f prime of C is equal to f of 4 minus f of negative 2 all over 4 minus negative 2. And Joseph, here's where I write that 4 right there. And I do that just to keep my head straight. Well, now it's just a matter of plugging in. I've already computed f prime, so that part's easy.
Since we know our domain is greater than negative 2 and less than 4, can we just simplify that to 1?
Hey, that's a really good point. Did everybody catch his point? He's seeing the graph in his head and he's saying, look, let's make this not harder than we have to. This is what the graph of the absolute value of x plus 2 looks like. What's the slope? 1, exactly. But if you did not see that, you could still get it by plugging in values, because f of 4 is 6, and f of negative 2 is 0, and all of that over 6, and so we still get 1 anyway. Now we ask an interesting question. What are the solutions to this equation right here? Well, not really sure, so let me try to simplify it. Any ideas for simplifying? A couple of ways you could do it.
Multiply both sides by the denominator.
Sure. That's a move that we do a lot, multiplying both sides by the denominator. Yeah. So, interesting equation. What values of C make that equation true? All of them.
Except for negative.
Negative 2 works.
Above 0.
Which numbers satisfy
0 and above.
Numbers
real? Some real numbers, yeah.
C is greater than or equal to negative 2. Or greater than.
How do you say that? How do you think it?
Well, if we have a negative number that's less than negative 2 for C, then we get negative on the left and
Negative 1
positive.
doesn't
Yeah, we got any negative number left.
Yeah. Yes.
That's
Some
not what
of
I said.
you
I said
were.
less than negative 2, which means negative 3.
Well, 0 works and 1 works, 2 works.
That is greater than negative 2.
Oh,
So I
Negative
think,
2
anything
works
less than-
and greater than 0.
anything less
Well,
than
negative 2 doesn't work.
negative 2.
Negative 2 does work, bro.
So anything less than negative 2.
And 0 equals 0.
the absolute value of 0,
I
which
didn't
is
know
just 0
what you
equals
did
0.
But,
Find the function now, if it goes to
But
zero,
we
the
can't include
denominator is
negative
zero.
two.
ah, yes. Okay, we need to make this mathematical. We've done some kind of figuring stuff out. Now let's actually make it mathematical. We know things about absolute value. We know that the absolute value of something will be itself when that something is non-negative, right? So this will equal c plus 2 when c plus 2 is non-negative, which means that c is greater than or equal to negative 2. Remembering the definition of absolute value makes a lot of the confusion about absolute value go away. Now, the second point is Jackson's, and that is that when I examined my solutions more carefully, what I was trying to solve was the equation c plus 2 over the absolute value c plus 2 is equal to 1. Does c equals negative 2 solve that? No, that's a phantom point. So that any c greater than negative 2 actually works. Every single c in the interval negative 2 to 4 actually solves that equation. So this was an interesting result here. It was kind of like your horizontal line. You asked about the horizontal line, right? Yep. This is like the horizontal line in that every c has the right slope. Yep. Does that help?
Yeah.
Okay. One more thing. We've already done the hard work. Now, what about on the interval negative 3 to 3? Does the mean value theorem apply on the interval negative 3 to 3? No? Why not?
It's not different.
It fails to be differentiable at one point in the domain. It is not differentiable at x equals negative 2. And we did. We found f prime. This exists except at x equals negative 2. Done. Yep. And by the way, if I can see ahead of time that the derivative will not exist, I can say that and move on without having to check continuity. Right? If one condition fails, the whole theorem fails. Does this guarantee that there is no such C? No, it does not guarantee. In this case, is there such a C? Well, I wouldn't necessarily know unless I set it up. It turns out no, because the graph looks like this. Here's our f of 3 over here. Here's our f of negative 3. And you can see from the graph that there will be no tangent line that is parallel to that C. Because the graph hits a sharp corner, goes off in a different direction. It never smoothly turns like that. Better? Okay. How does this work in real life? In real life, what we use the mean value theorem for is to connect average rate of change to instantaneous rate of change. So maybe I have a situation where I know an average rate of change, and I use that, I leverage that to get some information about the instantaneous rate of change. Or maybe I have a situation where I have instantaneous rate of change, and I leverage that to get some information about average rate of change. So that's the big picture idea. Now let's see how this works out in practice. A man enters a 1,500 meter tunnel. A camera takes his picture. He exits. He exits 50 seconds later. A second camera takes his picture. Okay, so everybody's got the scene? Okay. 2 weeks later, he gets a picture.
Are we implying that the man runs all 1,500 meters in 50 seconds?
He's driving.
Oh, he's driving. All it says is a man enters, you know.
Oh gosh, that's like one of those bad dad jokes. I hit a deer the other day. He died instantly. I felt bad, but when I'm jogging, I'm in the zone.
Wow.
You say bullshit, but I'm just saying it is possible.
I hit a deer.
Okay. So here is our setup. A man enters a 1,500-meter tunnel. A camera takes his picture. He exits 50 seconds later. A second camera takes his picture. 2 weeks later, he gets a ticket for exceeding the 20 meter per second, which is about 45 miles per hour, speed limit. Why? The man might try to argue, you never caught me going greater than 20 meters per second. But the judge will say, yes, we did. Why is that? Because the information that is given right here and right here allow me to compute an average rate of change, specifically an average velocity. Does everybody see how I can do that? So I get an average rate of change like so.
You're running on over 50
So his average rate of change was 30 meters per second. Okay. Now we ask two simple questions. First of all, is your velocity a continuous function? Can you jump velocities?
No.
Yes.
Wait, I'm wrong. Thinking about the different levels here. Is your position a continuous function? Can you jump positions?
No.
Can you teleport?
No.
I wish.
Second, is your position a differentiable function? Can you find the derivative of position at all times?
Yes.
Yes.
Yeah, of course. That's called the velocity. Okay. So the position S of t or x of t. Yeah.
In a
But
tunnel.
but
Straight line.
but to do that, you would have to stop instantaneously in 0 time and then change your position
It would still look like that.
in
even if it
instantaneous
wasn't.
time. You can't really do that.
You can't do
in
that.
real life. So we have x of t is continuous on the time interval 0 to 50. Notice I'm looking at the time interval because my x is a function of t, right? Function of distance. And it is also differentiable on the interval 0 to 50. And therefore there must be a c somewhere between 0 and 50, such that x prime of c, what's another spelling for x prime? V, the velocity, has to equal x of 50 minus x of 0 all over 50 minus 0. Now, look at that carefully. What is that? That's just delta x over delta t. That's equal to 1,500 minus 0 over 50 minus 0, which is 30 meters per second. What does the mean value theorem do for us? It means that since his average rate of change was 30 meters per second in the tunnel, there had to have been a time when his actual speed was 30 meters per second in the tunnel. Or higher. Or possibly higher, right? But 30 is enough. This actually happened to a friend of mine. She went to Austria, and she made the mistake of getting a little zippy sports car. And she opened it up in a tunnel, and she got a ticket later that she had to pay in shillings.
Shillings.
Yeah,
So 30 meters per second.
65.
It's faster than you want. And be able to stop and wait like 10 seconds.
That's what they do in Europe, actually. They
Does this make sense here, how we are connecting average rate of change to instantaneous rate of change? Yes? No?
That would be just a horizontal line, like you're going 30 miles per hour.
You don't have to be necessarily. There are all sorts of different ways you can do it. You could do it,
But with the information given, it'd be a straight line. Right.
no, not necessarily. You could do it like this at 30. You could do it like this where you start at 20 in the tunnel, at the beginning of the tunnel, and you go up, over, and slow back down to 20. So you're trying to fool the radar, blah, blah, blah. And as long as you do it in any such way so that your delta x over delta t is 30 meters per second, it is guaranteed that you have to cross through that point right there at some point. So it doesn't tell you where. It doesn't tell you when. I don't know when in the tunnel it happened. I just guarantee that it happened at some point. Okay? So the the mean value theorem allows me to be smart and capture at least one instantaneous rate of change during that time. How are we doing so far? Sua, do you have a question? Okay. All right, fair enough. Let's look at the other way. Suppose I have a function whose derivative is 0 for every single x in the interval a to b. What can I say about f of x? Now, before we answer this question, what I'd like for you to do is to try to draw a function whose derivative is 0. In your notes, please. Draw a function whose derivative is 0 for every single point on the interval a to b.
Is it discontinuous or it exists?
Well, I'm just asking you to draw a function so that f prime is equal to 0 for every point on a to b. Is f prime equal to 0 for every point in a to b? No. Got a couple people thinking about it. A couple people who have it. How many of you have a function? No. Okay. How many of you drew a horizontal line? Is it possible to draw any other function other than a horizontal line? No. Okay, so intuitively we think that if my f prime is 0, then my function has to be a constant function.
No, that's not continuous. And
The derivative would be this. Yeah. Interesting. So I claim that f of x is equal to a constant value. Now it's obvious the other way. If f of x is constant, clearly the derivative is 0. But how do I go in the reverse direction? How do I go from f prime is equal to 0 to say that f of x equals constant? The mean value theorem is going to do that for me. The proof is really simple. Proof. Since f prime of x is equal to 0, does my derivative exist on every point on a to b? Yes. Yes. So f of x is differentiable on a to b. Notice the closed interval, that's okay. It includes the open interval. And since it is differentiable on a to b, what else do I know about f automatically? It is continuous on a to b because differentiability implies continuity. There we go. So notice, Earl, the discussion you raised here, I appreciate you raising that, because that discussion about could there be a jump was related to the reasoning that we used right here. Since f prime is 0, it has a derivative, and since it has a derivative, it's continuous on every place where it has a derivative. Well, that means it meets the conditions of the mean value theorem, right? So there is a C somewhere in A to B such that f prime of C equals f of B minus f of A over B minus A. Right? Now, here's the thing. F prime of C is equal to 0. How do I know that? Because f prime of x is equal to 0 at every point. So that gives me, whoops, spelled that wrong. That gives me already that this fraction is equal to 0. If I have a fraction equal to 0, what has to be true about that fraction? The numerator is 0. And if the numerator is 0, then that means that what has to be true about f of b and f of a? They have to be the same. But wait, there's more. That gets me that f of b is equal to f of a. That's just the inputs, here and here. But what if I take any 2 points, let's say C and D, on the inside? Same argument. Take any let's make them D and E, in between A and B. Then f is certainly continuous and differentiable on the interval D to E. So there has to be a C somewhere between D and E, such that f prime of C is equal to f of D minus f of E all over D minus E, which is necessarily 0. And what does that mean? That means that f of D has to equal f of E. Now this proof here has a fair amount of scribbling, but we can express it like this. If I take any 2 points, the average rate of change between those 2 points has to equal the instantaneous somewhere, and the instantaneous is 0. So that by having a 0 rate of change instantaneously, I am forcing the average rate of change to be 0 everywhere as well. Taking information about the instantaneous, and I'm moving it over into information about the average. Does that make sense? We call this the bump principle, by the way. If my function had a bump somewhere up here, then its average rate of change would not be 0 on the bump, which means the instantaneous rate of change would have to be non-zero somewhere in between.
So then, if we're proving, say, a problem like this, then what would we put? Would we put there is a C on the interval A to B such that f prime C, so forth, or would we do the?
I'll tell you what, we're actually going to see this theorem again when we come back and do antiderivatives. So don't.
Did you say anti-derivative?
Uh-huh.
integrals?
I just wanted to.
Is that the thing that included S?
Yes.
So rather than worry about it at this time, I want you to just understand the concept, which is that we're taking information about the instantaneous rate of change and turning it into information about the average. Okay? Yes, Brian. Yep.